Today's topic is applications of operational amplifier. There are several applications of operational amplifier. This is the first application, inverter. How an operational amplifier can be used as an inverter. To use an operational amplifier as inverter, this is the circuit diagram. Here operational amplifier is used as basic inverting operational amplifier, in which non-inverting terminal 2 is grounded. Input signal voltage Vs is applied to the inverting terminal 1 through impedance Z, and feedback from output to inverting terminal is through impedance Z dash. Output voltage is VO. From the theory of inverting operational amplifier, we know that virtual short circuit exists at input terminals, and we have expression for VO upon Vs as VO upon Vs equal to minus Z dash upon Z. Z dash is impedance through which feedback from output is added to inverting terminal 1, and Z is impedance through which input signal voltage Vs is applied to inverting terminal 1. So ratio of output voltage VO and input voltage Vs is equal to minus ratio of these two impedances Z dash and Z. V output upon Vs equal to minus Z dash upon Z. If Z dash equal to Z, then we have V output upon Vs equal to minus 1, that is V output equal to minus Vs. That is simply the sign of input has been changed. So output of this operational amplifier will be equal to that of its input Vs multiplied by minus sign. So only sign is changed. Hence, such a circuit acts as a phase inverting amplifier, an amplifier which invert the phase of input signal, and it is known as a sign changer or inverter. Next application is scale changing amplifier. In the above circuit of inverting operational amplifier, if Z dash equal to NZ, that is, if we consider Z equal to R, not NR, Z equal to R, so that and Z dash equal to NR, then we have Z dash equal to NZ, Z equal to R and Z dash equal to NR. Z dash is equal to NZ. In this case, V output will becomes equal to minus NVS. Thus, the scale has been multiplied by a factor of minus n. Such amplifier is known as scale changing amplifier. So the circuit is same, only values of Z and Z dash are different for these two applications. First one was inverter, in which only phase is changed. Impedances Z and Z dash are same, and in scale changing amplifier, the relation between two impedances is such that Z dash equal to NZ, so that output voltage is obtained, which is minus n times that of input voltage, VO equal to minus NVS. And now scale is changed and it is multiplied by minus n times. Next application is phase shifting amplifier. Circuit is again the same, but now impedances Z and Z dash are chosen so that their amplitudes are same. Mode Z is same for Z and Z dash, but their phase angles are different. We take Z as mode Z e to the power I theta. Mode Z is its amplitude and theta represent the phase. Similarly, Z dash is equal to mode Z e to the power I phi. So we see that in Z and Z dash their amplitudes are same, equal to mode Z. Their phases are different. In expression for Z we have e to the power I theta. Theta is phase, and in expression for Z dash we have e to the power I phi. So phi is the phase for impedance Z dash and theta is the phase for impedance Z. In this case, this ratio of output voltage to input voltage VO upon Vs, which was equal to minus Z dash upon Z. Now substituting the values of Z dash and Z, we have this expression. For minus sign, we write e to the power I pi. E to the power I pi is equal to minus 1. E to the power I theta is cos theta plus I sin theta. So e to the power I pi is cos pi plus I sin pi. Sin pi is 0 and cos pi is minus 1. So for minus 1 we can write e to the power I pi, and remaining ratio of e to the power I phi and e to the power I theta is e to the power I phi minus theta. So this ratio now comes out to be e to the power I pi plus phi minus theta. So now the phase is changed by pi plus phi minus theta. So phase change of pi plus phi minus theta is obtained. Thus the operational amplifier shifts the phase of a sinusoidal input voltage without affecting its amplitude. Such amplifier is known as phase shifting amplifier. Next application is summing amplifier. An amplifier which can make sum of two or more voltages, input voltages. This application is shown in this figure. This is also inverting amplifier. Non-inverting input terminal, that is represented by plus sign, is grounded, and at inverting terminal, that is represented by minus sign, three input voltages V1, V2 and V3 are applied through resistances R1, R2 and R3 respectively. V1 voltage is applied to inverting terminal through resistance R1. V2 voltage is applied to the inverting terminal through resistance R2, and V3 voltage is applied through resistance R3. Feedback resistance is R2. So in this case, feedback of output voltage is applied through the inverting to the inverting terminal through resistance R2. In this case, we have from this relation for basic inverting amplifier, VO upon Vs equal to minus Z dash upon Z. From this relation, we have VO upon Z dash equal to minus Vs upon Z, and here Z dash is equal to R2. Z dash is impedance through which feedback is added. Here for Z dash we have resistance R2. So VO upon Z dash is equal to VO upon R2. And from this relation we have VO upon Z dash equal to minus Vs upon Z. Then here in right hand side we have minus Vs upon Z, and minus Vs upon Z is equal to sum of these three terms, V1 upon R1 plus V2 upon R2 plus V3 upon R3. This is the sum of three input currents. Vs upon Z is current through input, and it is equal to V1 upon R1 plus V2 upon R2 plus V3 upon R3. V1 upon R1 is current through resistance R1. V2 upon R2 is current through resistance R2 and V3 upon R3 is current through resistance R3. So we can write VO as equal to minus bracket R2 upon R1 into V1, capital R2 upon small r2 into V2 plus capital R3 upon small r3 into V3. If if all these input resistances R1, R2 and R3 are equal and equal to small r, then we can write this expression as VO equal to minus R2 capital R2 upon small r into V1 plus V2 plus V3, so that output voltage obtained will be proportional to the sum of three input voltages. VO is proportional to V1 plus V2 plus V3. So for this application it is required that three input resistances R1, R2, R3 must be the same. So here output voltage is proportional to the sum of input voltages, hence the circuit behaves as a summing amplifier. This circuit is widely used to form linear combination of various signals in analog computers. It can be used to get an output voltage which is proportional to the linear combination of input voltages. VO is proportional to the linear combination of V1, V2 and V3. Next application is voltage follower. In this application, operational amplifier is used as non-inverting operational amplifier. Here input signal voltage Vs is applied to the non-inverting terminal plus, represented by plus sign. It is non-inverting terminal, and input voltage Vs is applied to the non-inverting terminal. From the theory of non-inverting operational amplifier, we know that ratio of output voltage to input voltage VO upon Vs equal to VO upon V1 equal to R plus R dash upon R. Here there is no current flows through the two input terminals, so input voltage Vi is 0. So in this case input signal voltage Vs will be equal to the voltage V1 which appear at inverting terminal. Voltage applied at non-inverting terminal will be equal to the voltage at non-inverting terminal, so that input voltage Vi is always 0 for this type of non-inverting operational amplifier. So here Vi is 0 and Vs equal to V1. So the ratio of output voltage to input voltage VO upon Vs equal to VO upon V1. Vs is equal to V1. And the ratio of VO and V1 is equal to ratio of R plus R dash and R. R plus R dash is the resistance at which output voltage is obtained, and R is the resistance across which voltage V1 is obtained. Output voltage is obtained between ground and the series combination of R and R dash. So it is equal to R plus R dash. So VO upon V1 equal to R plus R dash upon R. If we put R dash equal to 0, then VO upon Vs will become equal to 1, that is VO equal to Vs. So in this case output voltage will be same as that of input voltage Vs. Such type of circuit is known as voltage follower, because the output voltage follows the input voltage and the circuit acts as voltage follower. Next application is integrator. To use operational amplifier as an integrator, circuit is shown in this figure, and we see that it is also an inverting operational amplifier. And now feedback impedance, in place of feedback impedance Z dash, we have a capacitor having capacity C. So to use an operational amplifier as an integrator, we use a capacitor C in place of feedback impedance Z dash. An integrator is shown in above figure. It is an inverting operational amplifier in which feedback impedance has been replaced by a capacitor C. Feedback through the capacitor C forces a virtual ground to exist at the inverting input terminal, that is output voltage VO is simply the voltage across the capacitor C. Output voltage obtained is VO, and it is equal to the voltage across this capacitor C. If Q is the charge on capacitor C and C is its capacity, then output voltage VO will be equal to minus Q upon C. From the relation Q equal to CV, if C is the capacity of the capacitor, then the charge at its plates Q is equal to CV. From the relation Q equal to CV, we have V equal to Q upon C, but here a minus sign is introduced because we see that current flows from the direction of inverting terminal to output terminal. So output voltage is taken as negative. VO is equal to minus Q upon C in place of Q upon C from the relation Q equal to CV and introducing a negative sign, and we use the relation for Q equal to integral I dt. This relation is obtained from the definition of current I. Current I is equal to dq upon dt, so that dq equal to I dt and charge Q will becomes integral I dt. So now output voltage VO, which is function of time, now it is equal to minus 1 upon C integral I dt, and limits of integral are 0 to t. Integral is for time t, so limits are taken as 0 to t. Since input current to the ideal amplifier is 0, we have I equal to Vs upon R. Input voltage Vs and current I, which flows through inverting terminal through resistance R, is given by this relation. Current I equal to V upon R, so I equal to Vs upon R. Vs is the input signal voltage applied between ground and inverting terminal, and resistance is R, so I equal to Vs upon R. Substituting this value of I in above relation, we have expression for output voltage as VOT equal to minus 1 upon RC integral 0 to T VST dt. Thus the output voltage is proportional to the integral of the input voltage. VO is proportional to integral Vs dt. It is proportional to the integral of input voltage Vs. If initial voltage is set equal to 0, Vs at time t equal to 0 is set equal to 0, and input voltage is constant equal to Vs, then we have VO equal to minus Vst upon Rc. If input voltage Vs is constant and initial voltage is taken as 0, then this integral value of this integral Vs dt limit 0 to t will becomes equal to only Vst. Vs is constant taken outside the integral, and integral dt is equal to t. In this case, VO is proportional to time t. Thus, output rises linearly with time. This type of voltage VO, which is proportional to time t, there is linear relation between VO and time t. This is known as a ramp, and it is called Miller sweep. Last application is differentiator. Differentiator is shown in this figure. It is an inverting operational amplifier. Now capacitor C is used in place of impedance Z, through which input signal Vs is applied to the inverting terminal, and R is the resistance in place of Z dash, through which feedback from output to added to the inverting terminal minus. It is an inverting operational amplifier in which input impedance has been replaced by a capacitor C. Because of virtual ground at the inverting terminal, we have I equal to dq upon dt. I is the current flowing through this capacitor C due to input signal voltage Vst applied at inverting terminal minus, between inverting terminal minus and ground. This current I flowing through capacitor C is given as I equal to dq upon dt. It is the definition of current, and here charge Q is the charge across the plates of capacitor C, and this charge Q is given by relation Q equal to Cv, so it is becomes equal to CVST. So it becomes C dVs upon dt. The output voltage VOT is equal to minus Ri. I current which flows through capacitor C. This current I is also flowing through resistance R, through which feedback is added. Because there is virtual ground between two input terminals, inverting and non-inverting terminals, no current flows through these two terminals between minus and plus. So entire current I which flows through capacitor C will also flow through resistance R. And now output voltage VO from the relation V equal to IR, we have VO equal to minus RI. Minus sign is used due to direction of current I. It flows from inverting terminal to output terminal. So output voltage is negative of IR. Substituting the value of I from above relation, we get output voltage equal to minus RC dVs upon dt. Thus, the output voltage is proportional to the time derivative of the input voltage. VO is proportional to dVs upon dt. Output voltage is proportional to differentiation of input signal voltage Vs. So this circuit is known as differentiator.